Hello and welcome to another peaceful journey through the mathematical universe, where we'll explore one of the most captivating and profound discoveries in modern science. I'm delighted you've joined me tonight for what promises to be a fascinating exploration of chaos theory and the famous butterfly effect, a concept that reveals how the tiniest changes in our world can ripple outward to create consequences of staggering magnitude. Tonight, as you settle into your favorite reading spot or nestle beneath the covers preparing for sleep, we're going to embark on an intellectual adventure that spans from the flutter of a butterfly's wings in Brazil to tornadoes in Texas, from the rounding of numbers in a 1960s computer to the fundamental limits of prediction itself. We'll discover how a simple mathematical mistake led to one of the most important scientific revelations of the 20th century, forever changing our understanding of predictability, determinism, and the delicate interconnectedness of everything in our universe. The story we're about to explore challenges some of humanity's most basic assumptions about cause and effect, order and chaos, predictability and randomness. It reveals a universe far more mysterious and interconnected than our ancestors could have imagined. A place where the smallest actions can trigger cascading sequences of events that reshape entire weather systems, alter the course of history, and transform the trajectory of individual lives in ways that seem almost magical in their improbability. As we begin this gentle exploration together, let me invite you to relax completely. Feel the weight of the day's concerns lifting from your shoulders as we prepare to dive into a realm where mathematics meets poetry, where scientific precision encounters profound mystery, and where the simple act of observation can fundamentally change our understanding of reality itself. Tonight's journey will take us through concepts that have revolutionized fields ranging from meteorology to economics, from ecology to psychology, revealing the beautiful and sometimes unsettling truth that we live in a world where small causes can have enormous effect. Our story begins on a cold winter morning in 1961, in a modest office at the Massachusetts Institute of Technology, where a meteorologist named Edward Norton Lorenz was working on what seemed like a straightforward problem predicting the weather. Lorenz, like many scientists of his era, believed deeply in the deterministic vision of the universe inherited from Isaac Newton. The idea that if you knew the exact position and velocity of every particle in the universe, you could predict the future with perfect accuracy. Weather, he reasoned, might be complex, but it was still just the interaction of air molecules following the laws of physics. With enough computing power and accurate measurements, forecasting should be possible indefinitely into the future. Lorenz had constructed a simplified mathematical model of the atmosphere using 12 differential equations that described relationships between temperature, pressure, humidity, wind speed, and other meteorological variables. His early computer, Real McBee LGP30, that was roughly the size of a desk and possessed less computing power than a modern digital watch, would churn through these calculations and print out long columns of numbers representing the evolving state of his simulated atmosphere. Each row showed the weather conditions at a particular moment in time, and watching these numbers change was like watching a mathematical weather system evolve on paper. On this particular morning, Lorenz wanted to examine a specific weather sequence more closely. Rather than starting his simulation from the very beginning, he decided to save time by starting from the middle of a previous run. He typed in the numbers that his computer had printed out earlier, set the machine running, and went to get a cup of coffee. When he returned an hour later, expecting to see the same weather pattern he had observed before, he was stunned by what appeared on the printout. The new simulation started out identically to the previous one, with the same temperatures, pressures, and wind patterns. But gradually, almost imperceptibly at first, the two simulations began to diverge. By the time the simulation had progressed 2 months into its imaginary future, the weather patterns were completely different. Where the original run showed clear skies, the new one showed storms. Where the first predicted high pressure, the second showed low pressure. It was as if he were looking at the weather on two completely different planets. Lorenz's first thought was that his computer had malfunctioned. Perhaps one of the vacuum tubes had failed, or there was an error in his programming. But after checking and double-checking everything, he discovered the true cause of the divergence. The computer performed its calculations to 6 decimal places, but to save space, the printout only showed 3 decimal places. When Lorenz had re-entered the numbers, he had unknowingly introduced tiny differences in the 4th, 5th and 6th decimal places. The number he entered as 0.56, for example, was actually 0.506127 in the computer's memory. This difference, less than 1 part in 1,000, seemed utterly insignificant. It was equivalent to the difference in pressure caused by a particle of dust, or the atmospheric disturbance created by a butterfly flapping its wings. Yet this microscopic change had completely transformed the behavior of his simulated atmosphere within just a few weeks of simulated time. Lorentz realized he had stumbled upon something profound, even in a completely deterministic system, where every outcome was theoretically predictable from initial conditions. Tiny uncertainties could grow exponentially until they completely dominated the system's behavior. This discovery struck at the heart of the scientific worldview that had dominated thinking since Newton's time. The Newtonian universe was a cosmic clockwork, where every effect had a clearly proportional cause. If you pushed harder on something, it moved faster. If you heated something more, it got hotter. The idea that infinitesimal causes could produce enormous effects seemed to violate our basic intuitions about how the world works. Yet here was mathematical proof that in certain types of systems, the relationship between cause and effect could be wildly disproportionate. Lorentz began to explore this phenomenon more systematically. Simplifying his weather equations down to their essential components, he eventually arrived at a system of just 3 differential equations that could exhibit the same type of sensitive dependence on initial conditions. These equations, now known as the Lorentz equations, describe a simplified model of atmospheric convection, essentially a mathematical representation of what happens when you heat fluid at the bottom and cool it at the top, creating the kind of circulation patterns that drive weather systems. When Lorentz plotted the behavior of these simplified equations in 3-dimensional space, something beautiful and mysterious emerged. Rather than settling into a fixed point or repeating in a simple cycle, the system traced out an infinitely complex trajectory that never quite repeated itself. The path it followed had an elegant, butterfly-like structure, 2 wing-shaped regions that the system would visit unpredictably, sometimes circling one wing for a while before suddenly switching to the other. This strange object, now known as the Lorentz attractor, became one of the most famous mathematical objects of the 20th century. It revealed that between the simple order of predictable systems and the complete randomness of truly chaotic systems lay a new category of behavior, deterministic chaos. These systems followed precise mathematical rules, but their behavior was so sensitive to initial conditions that they appeared random and unpredictable to any observer who couldn't measure those initial conditions with infinite precision. The implications of Lorentz's discovery extended far beyond meteorology. Scientists began to realize that sensitive dependence on initial conditions might be a fundamental feature of many natural systems. The flapping of a butterfly's wings might indeed, through a series of increasingly complex interactions, influence the formation of weather systems on the other side of the globe. This insight led Lorentz to pose his famous question in a 1972 lecture: does the flap of a butterfly's wings in Brazil set off a tornado in Texas? This question captured the public imagination precisely because it seemed to overturn our common-sense understanding of causation. We're accustomed to thinking that small causes have small effects and large causes have large effects. When we see a massive tornado, we naturally look for equally massive causes, powerful pressure systems, colliding air masses, or dramatic temperature differences. The idea that such a devastating event might be triggered by something as delicate as a butterfly's wing beats challenges our fundamental assumptions about how the world works. The butterfly effect, as this phenomenon came to be known, represents more than just a curious mathematical anomaly. It reveals deep truths about the structure of reality itself. In our daily lives, we make countless small decisions and take countless small actions, mostly without considering their long-term consequences. We choose to take one route to work instead of another. We decide to call an old friend or put it off until tomorrow. We pick up a book that catches our eye or leave it on the shelf. The butterfly effect suggests that some of these seemingly trivial choices might have consequences that ripple forward through time in ways we could never predict or imagine. Consider the famous example of Archduke Franz Ferdinand, whose assassination in Sarajevo in 1914 triggered a chain of events that led to World War I, fundamentally reshaping the political map of Europe and setting the stage for many of the conflicts that would define the 20th century. The assassination itself might never have happened if the Archduke's driver hadn't made a wrong turn, bringing the car directly in front of the assassin Gavrilo Princip, who had given up on his mission and was eating a sandwich at a cafe. A simple navigation error, the kind of small mistake we all make regularly, became the trigger for a global catastrophe that killed millions and changed the course of history. Or consider the discovery of penicillin by Alexander Fleming in 1928. Fleming had left a bacterial culture plate uncovered by accident, and when he returned from vacation, he found that mold had contaminated the culture. Rather than simply discarding the ruined experiment, Fleming noticed that the bacteria around the mold had died. This accidental observation led to the development of the first antibiotic, saving countless millions of lives throughout the 20th century. A moment of carelessness in laboratory hygiene became one of the most important medical discoveries in human history. These historical examples illustrate how the butterfly effect operates not just in mathematical equations or weather systems, but in the complex web of human society. Individual actions, seemingly insignificant at the moment they occur, can cascade through networks of causation to produce outcomes of tremendous significance. The young man who decides to apply to a particular university, where he meets the woman who becomes his wife, whose encouragement leads him to pursue a career in medicine, where he makes a discovery that saves thousands of lives. Each step in this chain seems ordinary and unremarkable, yet together they create a trajectory of enormous consequence. The mathematical foundation of the butterfly effect lies in the concept of sensitive dependence on initial conditions, which can be understood through the lens of phase space, a mathematical construct that represents all possible states of a dynamic system. Imagine a simple pendulum swinging back and forth. At any given moment, the pendulum's state can be completely described by two numbers: its position, how far it has swung from vertical, and its velocity, how fast it's moving and in which direction. If we plot position on the horizontal axis and velocity on the vertical axis, every possible state of the pendulum corresponds to a single point in this two-dimensional phase space. For a regular pendulum with friction, the phase space trajectory spirals inward toward a single point representing the pendulum at rest. No matter where you start the pendulum swinging, it will always end up at the same final state. This is an example of a system with a point attractor. All trajectories are drawn toward the same final destination. Such systems are highly predictable. If you know the current state, you can predict the final state with certainty, and small changes in initial conditions produce correspondingly small changes in outcomes. But chaotic systems like the Lorentz equations behave very differently in phase space. Instead of converging toward a simple point or cycling through a regular pattern, chaotic trajectories trace out incredibly complex, never-repeating paths through phase space. Two trajectories that start arbitrarily close together will initially follow nearly identical paths, but exponentially diverge until they bear no resemblance to each other whatsoever. This is the mathematical signature of chaos, deterministic behavior that is nevertheless unpredictable, due to sensitive dependence on initial conditions. The study of chaos theory has revealed that such behavior is far more common in nature than scientists initially realized. The double pendulum, simply two pendulums connected end to end, exhibits chaotic motion despite being governed by perfectly deterministic equations. Population dynamics in ecology often show chaotic behavior, with animal populations fluctuating in unpredictable ways that can lead to sudden extinctions or explosive growth. Even our solar system, long considered the paradigm of celestial clockwork, shows chaotic behavior over millions of years, making it impossible to predict the precise positions of planets indefinitely into the future. The dripping of a leaky faucet provides a beautiful example of how chaos emerges in everyday situations. At very low flow rates, drops form and fall in a perfectly regular rhythm, drip, drip, with each drop identical to the last. As you increase the flow slightly, the rhythm becomes period 2, large drop, small drop, large drop, small drop. Increase it a bit more, and you get period 4, large, medium, small, medium, large, medium, small, medium. But increase the flow just a little more, and suddenly the pattern becomes completely irregular. The timing between drops becomes unpredictable, and the size of each drop varies in apparently random ways. This transition from order to chaos can happen through infinitesimally small changes in flow rate, demonstrating how systems can suddenly shift from predictable to chaotic behavior. The implications of chaos theory extend deep into our understanding of prediction and control in complex systems. Weather forecasting provides the most famous example of these limitations. Despite having access to vast networks of weather stations, satellite data, and supercomputers capable of performing trillions of calculations per second, Meteorologists cannot reliably predict weather conditions more than about 10 days into the future. This isn't due to inadequate technology or insufficient data. It's a fundamental consequence of the chaotic nature of atmospheric dynamics. The atmosphere is so sensitive to small perturbations that even perfect measurements and perfect models would eventually fail due to the butterfly effect. This limitation has profound implications for many other fields that depend on prediction. Economic forecasting faces similar challenges because economic systems exhibit chaotic behavior. Stock markets can undergo sudden crashes or bubbles that seem to emerge from nowhere, triggered by the complex interactions of millions of traders responding to information, rumors, and psychological factors. Small changes in investor sentiment or minor policy announcements can cascade through global financial networks to produce major market movements that would have been impossible to predict in advance. Climate science faces a particularly interesting challenge related to chaos theory. While day-to-day weather is chaotic and unpredictable beyond about 10 days, long-term climate patterns can be more predictable because they depend on slower changing factors like ocean temperatures, ice cover, and atmospheric composition. It's a bit like trying to predict the position of a single air molecule in a room. Impossible versus predicting the average temperature of the room, quite feasible. Climate scientists can make reasonably confident predictions about global temperature trends over decades, while remaining unable to predict whether it will rain on a specific date next year. The study of chaos has also revolutionized our understanding of biological systems. The human heart, for example, normally beats with a slightly irregular rhythm that appears random but actually contains subtle chaotic patterns. Paradoxically, a perfectly regular heartbeat can be a sign of disease, while healthy hearts exhibit controlled chaos. This discovery has led to new approaches for detecting and treating cardiac arrhythmias based on chaos theory principles. Neural networks in the brain also exhibit chaotic behavior, with patterns of neural firing that are sensitive to tiny changes in initial conditions. Some researchers believe that this chaotic behavior might be essential for creativity and learning, allowing the brain to explore new patterns of thought and break out of rigid behavioral patterns. The edge of chaos, the boundary between order and disorder, might be the optimal regime for information processing in complex adaptive systems. Ecology provides countless examples of chaotic dynamics in natural systems. Predator-prey relationships, competition between species, and the spread of diseases through populations all can exhibit chaotic behavior. Small changes in birth rates, environmental conditions, or the introduction of new species can trigger dramatic shifts in ecosystem dynamics. The collapse of cod fisheries off the coast of Newfoundland in the 1990s provides a sobering example of how chaotic dynamics can lead to sudden, unexpected system failures that are nearly impossible to reverse. The mathematics underlying chaos theory reveals deep connections between seemingly unrelated phenomena. The same mathematical structures that describe the Lorentz attractor also appear in laser dynamics, chemical reactions, and the behavior of electronic circuits. This universality suggests that chaos is not just an isolated curiosity, but a fundamental mode of behavior that emerges naturally in many different types of complex systems. One of the most beautiful aspects of chaos theory is the discovery that chaotic systems often contain hidden order in the form of strange attractors. These mathematical objects have fractal structure, meaning they contain infinite detail at every scale of magnification. The Lorentz attractor, when examined closely, reveals an incredibly complex, intricate structure that never quite repeats itself yet follows a precise mathematical pattern. This suggests that even in the most unpredictable systems, there are deep organizing principles that constrain and shape the apparent randomness. The concept of fractals, intimately connected to chaos theory, has revealed that many natural phenomena exhibit self-similar structure across multiple scales. Coastlines, mountain ranges, river networks, blood vessels, lung structures, and lightning bolts all show fractal properties. When you zoom in on a coastline, the jagged irregularities you see at one scale are repeated at smaller and smaller scales, creating infinite complexity from simple mathematical rules. This fractal structure often emerges naturally from chaotic dynamics, suggesting deep connections between chaos, fractals, and the organization of natural systems. The butterfly effect has profoundly influenced our understanding of historical causation and the role of contingency in human affairs. Traditional historical analysis often focuses on major forces, economic trends, political movements, technological innovations as the primary drivers of historical change, but chaos theory suggests that chance events and individual decisions can sometimes have disproportionate historical consequences. The wrong turn that brought Archduke Franz Ferdinand into the path of his assassin, the contaminated petri dish that led to penicillin, the chance meeting that sparked a scientific collaboration, these small, seemingly insignificant events can redirect the entire course of human civilization. This perspective has important implications for how we think about free will and personal responsibility. If tiny actions can have enormous consequences, then every choice we make, no matter how trivial it seems, potentially influences the future in ways we cannot predict. The butterfly effect suggests that we live in a world where individual agency matters more than we might expect, but also where the consequences of our actions extend far beyond our ability to foresee or control them. The paradox of deterministic chaos systems that are completely deterministic yet utterly unpredictable has also influenced philosophical discussions about causation and reductionism. The traditional scientific approach involves breaking complex systems down into simpler components, understanding how each component works, and then predicting the behavior of the whole system from the behavior of its parts. But chaos theory reveals that this reductionist approach has fundamental limitations. Even if we understand every component of a chaotic system perfectly, we may still be unable to predict its long-term behavior due to sensitive dependence on initial conditions. This insight has led to the development of complexity science, which studies how complex behaviors and patterns can emerge from the interactions of many simpler components. Emergence, the appearance of higher-level patterns and behaviors that are not obviously predictable from lower-level rules, is now recognized as a fundamental feature of many natural and social systems. Traffic jams, stock market crashes, the formation of crystal structures, the development of consciousness, and the evolution of life itself, all involve emergent phenomena that arise from complex interactions and cannot be easily predicted from first principles. The butterfly effect has also influenced fields far removed from physics and mathematics. In psychology, chaos theory has been applied to understanding mood disorders, cognitive development, and therapeutic change. Small interventions in therapy, a single insightful comment, a moment of genuine empathy, a slight reframing of a problem can sometimes trigger profound and lasting changes in a person's mental health and life trajectory. The timing and context of these interventions often determine their effectiveness in ways that seem to follow chaotic dynamics. Social movements and political revolutions often exhibit butterfly effect dynamics, where small events trigger massive social transformations. The self-immolation of Mohamed Bouazizi, a Tunisian street vendor protesting police corruption, became the spark that ignited the Arab Spring, leading to the overthrow of governments across the Middle East and North Africa. Rosa Parks's refusal to give up her bus seat, a single act of individual defiance, became a catalyst for the American civil rights movement. These examples illustrate how individual actions, when they occur at the right time and place, can resonate through social networks to produce changes of historic magnitude. Technology and the butterfly effect intersect in fascinating ways in our increasingly connected world. The internet and social media have created new channels through which small perturbations can amplify into global phenomena. A single tweet can go viral and influence elections, stock prices, or social movements. A coding error in a small software component can cascade through interconnected systems to cause massive failures. The 2010 flash crash in financial markets, where the Dow Jones Industrial Average dropped nearly 1,000 points in minutes before recovering, was triggered by a single large trade that interacted with automated trading algorithms in unexpected ways. The COVID-19 pandemic provides a stark illustration of butterfly effect dynamics on a global scale. A virus that likely jumped from animals to humans in a single location spread through the interconnected networks of global travel to affect every country on Earth within months. Small differences in policy responses, individual behaviors, and random events led to dramatically different outcomes in different regions. The timing of when various countries implemented lockdowns, for example, often made the difference between manageable outbreaks and healthcare system collapse. Chaos theory has practical applications in many technological fields. Engineers designing structures must account for the possibility of chaotic vibrations that could lead to catastrophic failure. The Tacoma Narrows Bridge collapse in 1940 was caused by chaotic oscillations that amplified until they tore the bridge apart. Modern bridge designs incorporate chaos theory principles to ensure stability under a wide range of conditions. Cryptography and computer security also benefit from chaos theory. Chaotic systems can generate sequences of numbers that appear random, but are actually produced by deterministic algorithms. These pseudo-random sequences are essential for encryption, data security, and computer simulations. The sensitive dependence on initial conditions that makes chaotic systems unpredictable also makes them excellent sources of apparently random numbers for cryptographic applications. Medical applications of chaos theory have emerged in areas ranging from cardiac care to cancer treatment. Chaos-based analysis of heart rhythm can detect early signs of cardiac problems that might be missed by traditional diagnostic methods. Some researchers are exploring whether chaotic dynamics in cancer cell populations could be exploited to make tumors more vulnerable to treatment. The immune system itself exhibits chaotic dynamics, with complex feedback loops and nonlinear responses that determine whether the body successfully fights off infections and diseases. Environmental science has been profoundly influenced by chaos theory, particularly in understanding ecosystem dynamics and species interactions. The populations of many species fluctuate in chaotic patterns that can lead to sudden extinctions or explosive population growth. These dynamics are often driven by complex interactions between species, environmental variability, and human activities. Understanding chaotic behavior in ecosystems is crucial for conservation efforts and environmental management. Climate dynamics provides some of the most important applications of chaos theory in environmental science. While individual weather events are chaotic and unpredictable, climate patterns emerge from the statistical behavior of these chaotic systems over long time periods. Climate models must account for chaotic dynamics while still being able to make useful predictions about long-term climate trends. This requires sophisticated mathematical techniques that can extract predictable patterns from chaotic behavior. The study of chaos has also revealed important insights about the relationship between scale and predictability. Systems that appear chaotic at one time scale might show predictable patterns at longer or shorter time scales. For example, while day-to-day stock market movements appear random and chaotic, longer-term market trends might be more predictable based on economic fundamentals. Similarly, while individual weather events are chaotic, seasonal climate patterns show more regularity and predictability. Education and learning theory have been influenced by chaos theory in understanding how knowledge and skills develop. Learning often exhibits sudden jumps and nonlinear progress rather than smooth, continuous improvement. Small changes in teaching methods, learning environment, or student motivation can sometimes produce dramatic improvements in learning outcomes. This sensitivity to initial conditions suggests that personalized approaches to education, which account for each student's unique starting point and learning style, might be more effective than one-size-fits-all methods. The butterfly effect has important implications for decision-making and risk management in complex systems. Traditional risk assessment often focuses on identifying and mitigating known, quantifiable risks. But chaos theory suggests that some of the most significant risks come from unexpected interactions and cascading failures that are impossible to predict in advance. This has led to the development of new approaches to risk management that emphasize resilience, adaptability, and the ability to respond quickly to unexpected events rather than just trying to prevent all possible failures. Financial markets provide particularly clear examples of chaotic dynamics and the limitations of prediction. Despite enormous investments in mathematical models, computer algorithms, and data analysis, major market movements often seem to come out of nowhere. The 2008 financial crisis, various market crashes, and the emergence of speculative bubbles all demonstrate how small perturbations can cascade through interconnected financial networks to produce global consequences. This has led to new approaches to financial regulation that focus on systemic risk and the stability of the financial system as a whole rather than just the regulation of individual institutions. The butterfly effect has also influenced artistic and creative fields. Musicians, writers, and visual artists have explored chaotic dynamics as sources of inspiration and new forms of expression. Fractal art uses mathematical chaos to create intricate, beautiful patterns that exhibit infinite detail at every scale. Musical compositions based on chaotic algorithms can produce complex, evolving soundscapes that balance structure and unpredictability in aesthetically pleasing ways. Literature has long been fascinated with the idea that small events can have large consequences. Ray Bradbury's short story A Sound of Thunder, written in 1952, explores the idea that stepping on a butterfly during time travel could alter the entire course of history. This story, written years before Lorenz's discovery of sensitive dependence on initial conditions, shows how the butterfly effect concept resonates with human intuitions about causation and contingency. The philosophical implications of chaos theory extend to fundamental questions about free will, determinism, and the nature of causation. If tiny, uncontrollable factors can have enormous consequences, what does this mean for human agency and moral responsibility? Are we responsible for consequences of our actions that we could never have predicted or intended? Chaos theory suggests that we live in a universe where individual choices matter enormously, but where the consequences of those choices extend far beyond our ability to predict or control. Some philosophers have argued that chaos theory provides a middle ground between strict determinism and pure randomness. In a chaotic universe, the future is not predetermined in any practical sense. Even though it follows deterministic laws, this opens space for genuine novelty and creativity, while maintaining the regularity and lawfulness that make science possible. The future emerges from the complex interplay of countless factors, many of which are too small to measure or control, creating genuine openness and possibility within a lawful universe. The therapeutic implications of understanding the butterfly effect can be profoundly healing and empowering. Many people struggle with feelings of insignificance, believing that their individual actions don't matter in the face of vast social, economic, and environmental challenges. But chaos theory reveals that individual actions can sometimes have consequences far out of proportion to their apparent size. A single act of kindness, creativity, or courage might ripple forward through time to influence countless other lives in ways we can never fully know or appreciate. At the same time, the butterfly effect can help us develop more realistic expectations about our ability to control outcomes. If tiny, unmeasurable factors can dramatically influence the future, then we must accept that many consequences of our actions will always remain beyond our prediction or control. This perspective encourages a kind of thoughtful humility. We should act with care and consideration while accepting that we cannot foresee all the consequences of our choices. The study of chaos has also revealed the importance of timing in complex systems. The same action can have completely different consequences depending on when it occurs in the system's evolution. A medication given at the right time might save a life, while the same medication given at the wrong time might be ineffective or even harmful. A piece of advice offered at the right moment might change someone's life trajectory, while the same advice offered at a different time might be ignored or misunderstood. This sensitivity to timing highlights the importance of paying attention to the context and state of the systems we're trying to influence. Whether we're trying to help a friend, solve a social problem, or make a business decision, understanding the current state of the system and the potential leverage points for change can make our actions far more effective than simply applying more force or resources. The butterfly effect also suggests new approaches to leadership and organizational change. Rather than trying to control every aspect of a complex organization, effective leaders might focus on creating conditions that favor positive emergent behaviors. Small changes in culture, communication patterns, or incentive structures can sometimes produce large improvements in organizational performance. This approach recognizes that complex social systems have their own dynamics that cannot be completely controlled but can be influenced through careful attention to key leverage points. Network theory, closely related to chaos theory, has revealed how small changes can propagate through interconnected systems. In social networks, ideas, behaviors, and innovations can spread in viral patterns that follow chaotic dynamics. Understanding these network effects can help us design more effective interventions for public health, education, and social change. Sometimes targeting a few highly connected individuals can be more effective than trying to reach everyone equally. The concept of edge of chaos, the critical boundary between order and disorder, has important implications for optimizing complex systems. Many natural and artificial systems seem to operate most effectively when they maintain themselves at this critical point, where they have enough stability to maintain their structure, but enough flexibility to adapt and evolve. This principle has been applied to everything from neural networks and immune systems to organizational management and economic policy. Understanding chaos theory can also help us appreciate the beauty and complexity of the natural world. The intricate patterns of turbulent flows, The fractal structure of coastlines and mountain ranges, the unpredictable behavior of weather systems, all these phenomena reflect the deep mathematical principles underlying chaotic dynamics. Rather than seeing chaos as disorder or randomness, we can recognize it as a sophisticated form of natural organization that creates endless variety and complexity from simple underlying rules. The butterfly effect reminds us that we live in a universe full of surprises, where the future remains genuinely open despite being shaped by lawful processes. This openness creates space for creativity, innovation, and positive change, while also requiring us to remain humble about our ability to predict and control complex outcomes. In a chaotic universe, hope and action remain meaningful, precisely because small efforts can sometimes produce large positive changes. As we consider the implications of chaos theory for our daily lives, we might think differently about the choices we make and the actions we take. Every conversation we have, every decision we make, every small act of kindness or creativity sends ripples out into the world in ways we cannot fully predict. Some of these ripples will fade quickly, but others might amplify and combine with other influences to create changes far beyond what we could have imagined. This perspective encourages a kind of thoughtful engagement with the world that balances action with acceptance, effort with humility. We can work toward positive goals while remaining open to unexpected opportunities and outcomes. We can take our choices seriously while accepting that many factors beyond our control will influence the ultimate results of our actions. The butterfly effect also suggests the importance of paying attention to small details and subtle changes in the systems around us. Sometimes the most significant developments begin as barely noticeable shifts that only become apparent in retrospect. Developing sensitivity to these early indicators can help us recognize important changes before they become obvious to everyone else. In our personal relationships, understanding chaos theory might make us more aware of how small gestures and interactions can have lasting effects. A moment of genuine attention, a word of encouragement at the right time, or a small act of forgiveness might influence someone's life trajectory in ways we never fully appreciate. This awareness can motivate us to bring more consciousness and care to our daily interactions with others. The study of chaos has also revealed the importance of diversity and redundancy in creating resilient systems. Systems with many different components and multiple pathways for achieving their goals are often more stable than highly optimized systems with fewer options. This principle applies to ecosystems, economies, social systems, and even personal life strategies. Maintaining diversity and avoiding over-optimization can help systems survive unexpected perturbations and adapt to changing conditions. As our exploration of chaos theory and the butterfly effect draws toward its close, we're left with a profound appreciation for the subtle complexity and hidden interconnectedness of the world around us. The mathematical discoveries of Edward Lorenz and others have revealed that we live in a universe that is simultaneously deterministic and unpredictable, ordered and chaotic, simple in its underlying rules yet infinitely complex in its manifestations. The butterfly effect teaches us that we cannot predict the future with certainty, but it also shows us that our actions matter in ways we might never fully comprehend. In a chaotic universe, individual choices and small acts of creativity, kindness, and courage can ripple forward through time to influence the entire trajectory of the future. This is both humbling and empowering. Humbling because it reminds us of the limits of our knowledge and control. Empowering because it reveals the potential significance of our individual contributions to the unfolding story of the world. Tonight, as you prepare for sleep, you might reflect on the countless butterfly effects that have shaped your own life, the chance encounters that led to important friendships, the unexpected opportunities that changed your career path, the small decisions that led to major life changes. All of these illustrate the chaotic dynamics that weave through every human life. You are both the product of countless butterfly effects from the past and the creator of butterfly effects that will influence the future in ways you can never fully know. In your dreams tonight, you might imagine yourself as part of the vast, interconnected web of causation that connects every action to every other action across the fabric of space and time. You might see how your smallest gestures send ripples through this web, combining and interacting with the ripples created by billions of other conscious beings to create the ever-changing pattern of reality. You might sense how the flutter of butterfly wings connects to the formation of storms, how random mutations connect to the evolution of species, how individual choices connect to the course of history, The mathematics of chaos theory reveals that we live in a universe far more mysterious and wonderful than our ancestors imagined. It is a place where simple rules can generate infinite complexity, where tiny causes can have enormous effects, where the future remains genuinely open despite being shaped by precise mathematical laws. In such a universe, every moment contains infinite possibility, every choice matters in ways we cannot fully foresee, and every individual participates in the ongoing creation of reality itself. As you drift into sleep, carried along by the same chaotic dynamics that shape weather systems and galaxies, may you find peace in the knowledge that you are part of something larger than yourself, a cosmic process of creativity and emergence that has been unfolding for billions of years and will continue long after you are gone. The butterfly effect reminds us that we are all connected, that our lives matter in ways both large and small, and that the future remains beautifully uncertain, full of possibilities we have yet to imagine. Sweet dreams. Fellow participants in the great chaotic dance of existence, may your sleep be filled with the knowledge that tomorrow will bring new opportunities to create butterfly effects of your own, sending ripples of positive change out into the world in ways both subtle and profound. In the morning, chaos theory will still be revealing new secrets about the nature of reality, still showing us how small causes can create large effects, still reminding us that we live in a universe where every action matters, and every moment holds the potential for transformation. The exploration of chaos theory naturally leads us into the fascinating realm of strange attractors and their fractal geometries. Beyond the famous Lorentz attractor, mathematicians have discovered an entire menagerie of these mathematical objects, each with its own distinctive shape and behavior. The Heian attractor, discovered by Michel Heian in 1976, emerges from an even simpler system of equations yet creates a delicate, curved structure that resembles a bent line when viewed from afar, but reveals infinite fractal complexity when examined closely. The Ressler attractor, found by Otto Ressler, creates a beautiful spiral structure that looks like a ribbon twisted in three-dimensional space, with trajectories that circle around and through this ribbon in never-repeating patterns. Each of these strange attractors tells a story about how order and chaos can coexist in mathematical systems. They are called strange not because they are unusual or quirky, but because they possess a fractional dimension. They are more complex than simple curves or surfaces, but less complex than solid three-dimensional objects. This fractional dimensionality is a hallmark of fractal geometry, revealing that the boundary between different levels of complexity is not as clear-cut as we might have expected. The concept of fractal dimension revolutionized our understanding of natural complexity. Traditional geometry deals with objects that have whole number dimensions. Points are zero-dimensional, lines are one-dimensional, surfaces are two-dimensional, and solids are three-dimensional, but fractals live in the spaces between these familiar categories. A coastline, for example, has a fractal dimension somewhere between 1 and 2. It's more complex than a simple line but not quite as complex as a surface. The exact value depends on how jagged and irregular the coastline is, with more complex coastlines having dimensions closer to 2. This fractal perspective has transformed our understanding of natural phenomena across many scales. Clouds, mountains, trees, blood vessels, neural networks, and galaxy distributions all exhibit fractal properties. When we measure the length of a coastline, we get different answers depending on the scale of measurement we use. As we use smaller and smaller measuring rods to trace around every inlet and peninsula, the measured length grows without bound, approaching infinity. This coastline paradox, first noted by Lewis Fry Richardson and later formalized by Benoit Mandelbrot, reveals that some of the most basic questions about natural objects don't have simple answers. Mandelbrot's contributions to our understanding of complexity extend far beyond coastlines. His exploration of the famous Mandelbrot set, perhaps the most famous fractal of all, revealed infinite complexity hidden within a simple mathematical equation. The Mandelbrot set is defined by iterating the equation z equals z squared plus c for complex numbers, and determining which values of c cause the iteration to remain bounded. The boundary of this set creates one of the most intricate and beautiful objects in all of mathematics, with self-similar structures that repeat at every scale of magnification. The discovery of the Mandelbrot set was made possible by computer graphics, as its incredible complexity can only be appreciated through visual representation. As computers became more powerful, mathematicians could zoom deeper and deeper into the set, revealing new levels of detail that seemed to go on forever. Each zoom revealed smaller copies of the main set, surrounded by intricate spirals, seahorse-shaped structures, and delicate filaments that connected different regions. The boundary of the Mandelbrot set has infinite length, but finite area, embodying the paradoxical nature of fractal geometry. The mathematical beauty of fractals connects to deep questions about the nature of infinity and the relationship between simple rules and complex outcomes. The Mandelbrot set emerges from one of the simplest possible mathematical operations, squaring a number and adding a constant, yet it generates visual complexity that rivals anything found in nature or art. This suggests that complexity is not necessarily the result of complicated underlying mechanisms but can emerge naturally from the iteration of simple processes. The concept of self-similarity, central to fractal geometry, appears throughout chaos theory and natural systems. In mathematical fractals like the Sierpinski triangle or the Koch snowflake, exact self-similarity means that each part is an exact scaled copy of the whole. But in natural systems, we often find statistical self-similarity, where the statistical properties of parts resemble those of the whole without being exactly identical. This kind of self-similarity appears in everything from the branching patterns of rivers and blood vessels to the price fluctuations of financial markets and the distribution of galaxies in space. The study of power laws has revealed another universal pattern underlying many complex systems. Power laws describe relationships where one quantity varies as a power of another quantity, creating scale-invariant behavior that appears the same at every level of magnification. The distribution of earthquake magnitudes follows a power law, as does the distribution of city sizes, the frequency of words in languages, the size distribution of avalanches, and the connectivity patterns of many networks. These power law relationships often emerge from systems that exhibit self-organized criticality, a state where complex systems naturally evolve toward a critical point between order and chaos. Self-organized criticality, discovered by Purbach and his colleagues, explains how complex systems can spontaneously organize themselves into a critical state, where small perturbations can trigger avalanches of activity at all scales. The classic example is a sand pile. As you slowly add grains of sand to a pile, it eventually reaches a critical slope where adding just one more grain can trigger an avalanche. These avalanches follow power law distributions, with many small avalanches and few large ones, and the system maintains itself at this critical point without any external control or fine-tuning. This concept has profound implications for understanding natural disasters, economic crashes, and social upheavals. Forest fires, earthquakes, stock market crashes, and social revolutions all seem to follow similar power law patterns, suggesting that they emerge from systems that have self-organized to a critical state where large-scale events are inevitable but unpredictable in their timing and magnitude. The butterfly effect operates most dramatically in these critically organized systems, where small perturbations can trigger large-scale reorganizations. The mathematical framework of dynamical systems theory provides powerful tools for analyzing chaotic behavior across different fields. Phase portraits, Poincare sections, Lyapunov exponents, and correlation dimensions allow scientists to detect and characterize chaos in experimental data. The largest Lyapunov exponent, in particular, provides a quantitative measure of how quickly nearby trajectories diverge in a chaotic system. A positive Lyapunov exponent indicates chaos, with larger values corresponding to more rapid divergence and shorter prediction horizons. Bifurcation theory explains how systems transition from regular to chaotic behavior as parameters change. The period-doubling route to chaos, discovered by Mitchell-Feigenbaum, shows how a system can undergo a cascade of bifurcations where the period of oscillation doubles repeatedly until chaotic behavior emerges. This route to chaos appears in many different systems, from population dynamics to electronic circuits to chemical reactions, suggesting universal principles underlying the emergence of chaos. Feigenbaum's discovery of universal constants in the period-doubling cascade represents one of the most remarkable findings in chaos theory. Despite arising in completely different physical systems, the mathematical ratios governing period-doubling transitions are identical across all systems that follow this route to chaos. These universal constants, now called Feigenbaum constants, reveal deep mathematical structures underlying the transition from order to chaos, and represent one of the few truly universal features of nonlinear dynamics. The study of intermittency provides another window into how chaotic systems behave. Many chaotic systems exhibit periods of apparently regular behavior interrupted by chaotic bursts. This intermittent chaos appears in turbulent flows, laser dynamics, and neural activity, among other phenomena. The statistical properties of these intermittent bursts often follow power law distributions, connecting intermittency to self-organized criticality and scale-invariant behavior. Turbulence represents perhaps the most important unsolved problem in classical physics, and chaos theory has provided crucial insights into its nature. Turbulent flows exhibit chaotic behavior at many different scales simultaneously, creating complex patterns that resist simple mathematical description. The energy cascade in turbulence, where large-scale motions break down into smaller and smaller eddies until viscosity dissipates the energy as heat, follows scaling laws that reflect the fractal geometry of turbulent structures. The Navier-Stokes equations, which govern fluid motion, can exhibit chaotic solutions even though they are completely deterministic. Understanding when and why these equations produce turbulent versus smooth flow remains one of the most challenging problems in mathematics and physics. The Clay Mathematics Institute has offered a $1 million prize for proving that solutions to the Navier-Stokes equations exist and are smooth for all time, or for finding an example where they break down. This problem sits at the intersection of chaos theory, mathematical analysis, and practical engineering. Weather and climate dynamics provide perhaps the most familiar examples of chaotic behavior in the natural world. The atmosphere is a turbulent fluid system driven by solar heating and constrained by the rotation of the Earth, creating complex patterns of circulation that exhibit chaotic behavior on multiple time scales. Weather systems show sensitive dependence on initial conditions, making detailed forecasts impossible beyond about 10 days. While climate patterns emerge from the statistical behavior of these chaotic weather systems over longer time periods, the concept of climate attractors helps explain how climate can be predictable on long time scales even though weather is chaotic on short time scales. The climate system, despite its chaotic weather variations, appears to be attracted to certain preferred states that depend on slowly changing boundary conditions like solar radiation, atmospheric composition, and ice cover. Climate change represents a shift from one attractor to another as greenhouse gas concentrations alter the energy balance of the Earth system. Tipping points in the climate system represent particularly dangerous manifestations of the butterfly effect on global scales. Small changes in atmospheric or oceanic conditions could potentially trigger rapid transitions to very different climate states. The collapse of ice sheets, the shutdown of ocean circulation patterns, or the release of methane from thawing permafrost could all represent irreversible tipping points where the climate system rapidly reorganizes into a new state that would be extremely difficult to reverse. The application of chaos theory to biological systems has revealed the importance of nonlinear dynamics in everything from cellular biochemistry to ecosystem dynamics. Population cycles in many species exhibit chaotic behavior, with complex fluctuations that can lead to sudden population crashes or explosions. The interaction between predator and prey species often generates chaotic dynamics, with populations that never settle into stable equilibrium but instead follow complex, unpredictable trajectories through phase space. Cardiac dynamics provide a medically important example of chaos in biological systems. The healthy heart exhibits complex variability in its rhythm that contains chaotic elements, while certain types of heart disease are associated with overly regular rhythms that have lost their healthy variability. Chaotic analysis of heart rate variability has become a diagnostic tool for detecting various forms of cardiovascular disease and assessing the risk of sudden cardiac death. Neural networks in the brain exhibit chaotic dynamics that may be essential for information processing and learning. The edge of chaos, the critical boundary between order and disorder, appears to be optimal for neural computation, allowing networks to maintain stable memories while remaining flexible enough to process new information and adapt to changing conditions. Some researchers believe that consciousness itself may emerge from chaotic dynamics in neural networks, with the complex, ever-changing patterns of brain activity reflecting the chaotic nature of thought and awareness. The immune system represents another biological system where chaotic dynamics play important roles. The immune response involves complex feedback loops and non-linear interactions between different types of immune cells, creating dynamics that can exhibit chaotic behavior. Understanding these dynamics is crucial for developing new treatments for autoimmune diseases, cancer, and infectious diseases. Evolutionary dynamics also exhibit chaotic behavior, with populations evolving along unpredictable trajectories through fitness landscapes. Small genetic changes can sometimes have large evolutionary consequences, leading to rapid speciation events or evolutionary dead ends. The butterfly effect in evolution means that the history of life on Earth represents just one of countless possible trajectories through the space of biological possibilities. The study of genetic regulatory networks has revealed how chaotic dynamics can arise from the complex interactions between genes and their protein products. Gene expression can exhibit chaotic oscillations that may be important for cellular differentiation and development. Understanding these dynamics is crucial for synthetic biology efforts to engineer biological systems with desired behaviors. Economic systems provide compelling examples of chaotic behavior in human social systems. Financial markets exhibit many characteristics of chaotic systems, including sensitive dependence on initial conditions, fractal price patterns, and sudden regime changes that resemble bifurcations in dynamical systems. The efficient market hypothesis, which assumes that prices follow random walks, has been challenged by evidence of non-linear dynamics and deterministic chaos in financial data. Market crashes and bubbles can be understood as manifestations of the butterfly effect in financial systems. Small changes in investor sentiment, policy announcements, or external events can trigger cascading effects through interconnected financial networks, leading to dramatic price movements that seem disproportionate to their initial causes. The 2008 financial crisis exemplified how problems in one sector, subprime mortgages, could propagate through the global financial system to create a worldwide economic downturn. Behavioral economics and agent-based modeling have revealed how individual decision-making can aggregate to produce chaotic market dynamics. Even if individual investors are perfectly rational, their interactions can generate complex, unpredictable market behavior. The presence of feedback loops, herding behavior, and non-linear responses to information creates conditions where small perturbations can have large effects on market outcomes. Social dynamics more broadly exhibit many features of chaotic systems. The spread of information, ideas, and behaviors through social networks can follow chaotic dynamics, with small initial differences leading to dramatically different outcomes. Social movements, fashion trends, and cultural changes often exhibit the kind of unpredictable, non-linear behavior characteristic of chaotic systems. The emergence of collective behavior from individual interactions represents one of the most fascinating aspects of chaos theory applied to social systems. Flocking behavior in birds, schooling in fish, and crowd dynamics in humans all emerge from simple rules governing individual behavior, yet they can produce complex, adaptive collective behaviors that seem to require central coordination but actually arise spontaneously from local interactions. Traffic flow provides an accessible example of how chaotic dynamics emerge in human systems. Traffic jams often appear seemingly from nowhere, spreading backward through traffic streams in ways that resemble shock waves in fluid dynamics. Small perturbations, a single driver braking unnecessarily, a slight adjustment in traffic light timing, or a minor accident can propagate through traffic networks to create major congestion patterns. Urban dynamics and city growth also exhibit chaotic behavior, with small changes in zoning policies, transportation infrastructure, or economic conditions leading to dramatically different patterns of urban development. The butterfly effect in urban planning means that well-intentioned policy changes can sometimes have unintended consequences that completely reshape the character and functionality of cities. The application of chaos theory to technology has led to new approaches in engineering and computer science. Chaos-based communication systems use the unpredictability of chaotic signals for secure communication, while chaos theory has informed the design of more robust control systems that can handle unexpected perturbations. Understanding chaotic behavior is crucial for preventing catastrophic failures in complex technological systems. Artificial intelligence and machine learning have been influenced by chaos theory in several ways. Neural networks operate most effectively when they maintain a balance between order and chaos, allowing them to generalize from training data while avoiding both overfitting and underfitting. Chaos theory has also inspired new algorithms for optimization and search that use chaotic dynamics to explore solution spaces more effectively than traditional methods. The Internet and World Wide Web exhibit many characteristics of chaotic systems, with complex patterns of information flow, network growth, and user behavior that follow power law distributions and exhibit sensitive dependence on initial conditions. Understanding these dynamics is crucial for designing resilient network architectures and predicting how information spreads through online social networks. Chaos theory has practical applications in cryptography and computer security, where chaotic systems can generate pseudo-random sequences that are useful for encryption and authentication. The sensitive dependence on initial conditions that makes chaotic systems unpredictable also makes them excellent sources of apparent randomness for cryptographic applications. Manufacturing and industrial processes often exhibit chaotic behavior that must be understood and controlled to maintain quality and efficiency. Chaos theory has been applied to optimize everything from chemical reaction processes to supply chain management, helping engineers design systems that are robust against small perturbations and capable of adapting to changing conditions. The study of failure cascades in complex technological systems has revealed how the butterfly effect can lead to catastrophic system-wide failures. Power grid blackouts, internet outages, and transportation network disruptions often follow chaotic dynamics, where small initial failures propagate through interconnected systems to create large-scale collapses. Understanding these dynamics is crucial for designing more resilient infrastructure. Environmental applications of chaos theory extend beyond climate to include ecosystem management, pollution control, and resource management. Many environmental systems exhibit chaotic behavior that makes them difficult to predict and manage using traditional approaches. Chaos theory provides tools for understanding when environmental systems might undergo sudden shifts to alternative states and how to design management strategies that account for inherent unpredictability. Conservation biology has been influenced by chaos theory in understanding population dynamics and extinction risks. Small populations are particularly vulnerable to chaotic fluctuations that can drive them to extinction even in apparently stable environments. Understanding these dynamics is crucial for designing effective conservation strategies and predicting which species are most at risk. Agricultural systems exhibit chaotic behavior in crop yields, pest populations, and soil dynamics. Weather variability, pest outbreaks, and market fluctuations all contribute to the nonlinear behavior of agricultural systems. Chaos theory has informed the development of more sustainable farming practices that work with natural variability rather than trying to eliminate it entirely. Water resource management faces challenges from chaotic behavior in river flows, groundwater dynamics, and precipitation patterns. Small changes in land use, water extraction, or climate conditions can lead to large changes in water availability. Understanding these dynamics is crucial for managing water resources sustainably in the face of increasing demand and climate change. The psychology of chaos and complexity has emerged as a field studying how humans perceive, understand, and respond to chaotic systems. People often have difficulty reasoning about nonlinear relationships and tend to underestimate the potential for small causes to have large effects. This cognitive bias can lead to poor decision-making in complex situations where the butterfly effect is operating. Therapeutic applications of chaos theory have emerged in psychology and psychiatry. Some therapists use chaos theory concepts to understand how small interventions can sometimes produce large changes in clients' mental health and life circumstances. The timing and context of therapeutic interventions can determine their effectiveness in ways that mirror sensitive dependence on initial conditions in chaotic systems. Educational applications of chaos theory have influenced how we think about learning and teaching. Learning often exhibits sudden transitions and nonlinear progress rather than smooth, continuous improvement. Understanding these dynamics can help educators design more effective learning environments that account for the complex, unpredictable nature of human learning processes. Chaos theory has influenced art, music, and literature in profound ways. Artists have used chaotic algorithms to generate complex, beautiful patterns that capture something essential about natural complexity. Musicians have composed pieces based on chaotic dynamics that balance structure and unpredictability in aesthetically pleasing ways. Writers have explored themes of sensitive dependence and unpredictable consequences in works that reflect chaos theory concepts. The aesthetics of chaos reveal deep connections between mathematical beauty and artistic expression. Fractal art, generated by iterating simple mathematical equations, creates images of stunning complexity and beauty that rival anything found in nature. These images suggest that mathematical processes can be inherently creative, generating novelty and beauty through purely algorithmic means. The philosophy of chaos theory raises profound questions about determinism, predictability, and the nature of scientific knowledge. If the universe is fundamentally chaotic, what does this mean for the scientific project of understanding and predicting natural phenomena? Chaos theory suggests that there are fundamental limits to predictability that cannot be overcome simply by gathering more data or building better models. The relationship between chaos and free will has been explored by philosophers and scientists. Some argue that chaotic behavior in the brain might provide the physical basis for free will, creating genuine openness in human decision-making that is neither completely determined nor completely random. Others argue that chaos theory shows how deterministic systems can nevertheless produce unpredictable behavior, suggesting that free will and determinism might be compatible after all. Chaos theory has influenced religious and spiritual thought in various ways. Some see chaotic dynamics as evidence of divine creativity and freedom, while others find in chaos theory confirmation of ancient wisdom about the impermanence and interconnectedness of all things. The butterfly effect resonates with spiritual traditions that emphasize how small acts of compassion and mindfulness can have far-reaching positive consequences. The therapeutic potential of understanding chaos extends to personal development and self-help applications. Recognizing that small changes can have large effects can motivate people to make positive changes in their lives, knowing that modest efforts might lead to significant improvements over time. At the same time, understanding the inherent unpredictability of complex systems can help people develop more realistic expectations and greater tolerance for uncertainty. Chaos theory offers important lessons for leadership and management in complex organizations. Traditional command and control approaches often fail in chaotic systems because they assume that outputs are proportional to inputs. Effective leadership in chaotic environments requires understanding how to work with natural dynamics rather than against them, identifying leverage points where small changes can produce large improvements, and maintaining flexibility in the face of unpredictable outcomes. The study of emergence in complex systems has revealed how new properties and behaviors can arise spontaneously from the interactions of simpler components. Consciousness emerging from neural activity, life emerging from chemistry, and intelligence emerging from computation all represent examples of emergent phenomena that seem to transcend their underlying substrates. Understanding emergence is crucial for fields ranging from artificial intelligence to synthetic biology. Network science, closely related to chaos theory, has revealed universal patterns in the structure and dynamics of complex networks. Small world networks, scale-free networks, and hierarchical networks all exhibit different types of emergent behavior and respond differently to perturbations. Understanding these network structures is crucial for everything from designing efficient transportation systems to controlling the spread of diseases. The concept of phase transitions has been extended from physics to other fields where systems can undergo sudden changes between different states of organization. Social movements, scientific revolutions, and technological transitions often exhibit the characteristics of phase transitions, with periods of gradual change punctuated by rapid, dramatic reorganizations that seem to emerge from nowhere. Resilience engineering has emerged as a field that applies chaos theory concepts to designing systems that can survive and adapt to unexpected perturbations. Rather than trying to prevent all possible failures, resilient systems are designed to fail gracefully and recover quickly from disruptions. This approach recognizes that in complex systems, some failures are inevitable and focuses on building adaptive capacity rather than rigid control. The study of black swan events, rare but high-impact occurrences that are difficult to predict, connects to chaos theory through the recognition that complex systems can produce outcomes that seem impossible based on historical experience. The butterfly effect suggests that black swan events might not be as rare as they appear but might result from the amplification of small perturbations that we fail to notice or understand. Complexity economics has emerged as an alternative to traditional economic theory, recognizing that economic systems exhibit many characteristics of chaotic and complex adaptive systems. rather than assuming equilibrium and rational act. Complexity economics studies how economic patterns emerge from the interactions of many adaptive agents operating under conditions of limited information and bounded rationality. The application of chaos theory to medicine extends beyond cardiology to include neurological disorders, cancer dynamics, and infectious disease spread. Many diseases involve complex, nonlinear processes that exhibit chaotic behavior. Understanding these dynamics can lead to new therapeutic approaches that work with natural biological rhythms rather than trying to impose artificial control. Chaos theory has practical applications in agriculture and food production, where complex interactions between weather, soil, pests, and management practices create nonlinear dynamics that are difficult to predict and control. Sustainable farming practices often embrace variability and complexity rather than trying to eliminate them, working with natural cycles and feedback loops to maintain productive, resilient agricultural systems. The study of avalanche dynamics has applications ranging from snow safety to financial risk management. Many systems exhibit avalanche-like behavior where small perturbations can trigger large-scale reorganizations. Understanding the statistical properties of these avalanches can help predict and mitigate their effects in various contexts. Chaos theory has influenced sports science and performance optimization, where small changes in technique, training, or mental state can sometimes produce large improvements in performance. Athletes operating at the highest levels often exist at the edge of chaos, where peak performance requires maintaining a delicate balance between control and spontaneity. The study of synchronization in chaotic systems has revealed how complex systems can spontaneously coordinate their behavior despite operating chaotically. Fireflies flashing in unison, heart cells beating together, and neural oscillations in the brain all represent examples of chaos synchronization that creates coherent collective behavior from chaotic individual dynamics. Traffic flow optimization using chaos theory principles has led to new approaches for managing transportation networks that account for the nonlinear dynamics of traffic flow. Adaptive traffic control systems use real-time feedback to respond to changing conditions, recognizing that small adjustments in timing or routing can have large effects on overall system performance. The application of chaos theory to linguistics has revealed fractal patterns in language structure and power law distributions in word frequencies. These patterns suggest that language itself might be an emergent property of complex adaptive systems, with grammar and meaning arising from the interactions of speakers and listeners over time. Chaos theory has influenced archaeology and anthropology in understanding how cultural patterns emerge and change over time. Cultural evolution exhibits many characteristics of complex adaptive systems, with small innovations sometimes leading to major cultural transformations that spread through populations in unpredictable ways. The study of opinion dynamics and social influence has been informed by chaos theory, revealing how social systems can exhibit sudden shifts in collective opinion that seem to emerge from nowhere. Understanding these dynamics is crucial for everything from political campaigning to public health interventions that depend on changing social norms. Chaos theory has applications in architecture and urban planning, where understanding the complex dynamics of how people move through and use spaces can inform better design decisions. Buildings and cities are complex systems where small design choices can have large effects on functionality, sustainability, and quality of life. The study of creativity and innovation has been influenced by chaos theory, with research suggesting that creative insights often emerge from chaotic dynamics in neural networks and social systems. Understanding these processes can inform educational and organizational practices that foster innovation and creative problem-solving. As our expanded exploration of chaos theory draws to its close, we find ourselves immersed in a mathematical framework that illuminates the deepest patterns underlying complexity and change throughout the universe. From the microscopic dynamics of cellular biochemistry to the vast scales of cosmic evolution, from the intimate patterns of neural activity to the grand sweep of cultural transformation, chaos theory reveals the subtle mechanisms through which small causes can produce enormous effects. The journey we have taken together tonight spans multiple scales of existence and diverse fields of human knowledge, yet everywhere we look, we find the same fundamental principles at work: sensitive dependence on initial conditions, strange attractors, fractal geometry, power law distributions, self-organized criticality, and emergent complexity create a unified language for understanding phenomena that once seemed unrelated and inexplicable. This mathematical unity suggests something profound about the nature of reality itself. The universe appears to be organized according to principles that generate complexity and beauty from simplicity, novelty from repetition, and order from chaos. The butterfly effect is not just a curious mathematical phenomenon but a fundamental feature of how complex systems create the rich tapestry of patterns we observe in nature and society. Tonight, as you prepare for sleep, you carry with you the knowledge that you exist within an intricate web of chaotic dynamics that connects your smallest actions to the largest patterns of cosmic evolution. Every breath you take, every thought you think, every choice you make sends ripples through this web in ways you can never fully predict or control, yet which contribute to the ongoing creation of reality itself. In your dreams, you might find yourself floating through strange attractors and fractal landscapes, witnessing the birth of complexity from simple rules, experiencing the delicate balance between order and chaos that makes life possible. You might sense how your consciousness emerges from the chaotic dynamics of neural networks, how your creativity arises from the edge of chaos where new possibilities are constantly being born. The mathematics of chaos theory offers both humility and hope. It reminds us that we cannot predict or control all the consequences of our actions, yet it also reveals that our smallest gestures can sometimes have enormous positive effects. In a chaotic universe, every moment contains infinite possibility. Every individual choice contributes to the unfolding story of existence, and every person participates in the great collaborative creation of the future. Sleep well tonight, knowing that you are part of the magnificent complexity that emerges when simple laws give rise to infinite possibility. The butterfly effect will continue its work while you rest, weaving together the choices and actions of billions of conscious beings to create tomorrow's reality. In the morning, chaos theory will still be revealing new secrets about the nature of complexity and change, still showing us how beauty and meaning can emerge from the most unlikely beginnings. Good night, and may the gentle chaos of your dreaming mind explore new territories of possibility, carrying you peacefully through the night toward a dawn rich with unexpected opportunities and beautiful uncertainties. May you awaken refreshed and inspired, ready to create butterfly effects of your own in a universe where every small action matters and every moment holds the potential for profound transformation.